So without further ado, we'll turn it over to our stars, starting off with Brandon Trabucco from St. Helens Senior High School, who worked with Dr. Christoph Teuscher at PSU. And Brandon's talk, as you can see, is accelerated computational models for temporal pattern recognition. All right.
Hello, everybody. So as he said, my name is Brandon Trabucco, and I spent my summer working at Orchard Laboratory at Portland State University. And specifically, I spent my time designing specific algorithms that are really fast at learning patterns in audio, in video, and just in sequences of things. And actually, more specifically, by the end of the summer, I had invented my own algorithm that I'm going to share with you guys later. So the constraints of my project were to design an algorithm that learns temporal patterns. And what that means is when you're recording something on a camera, the pixels are constantly changing. And when you look at that image, you can see people walking around, you can see people waving their hands. Those are all patterns. Those are all events that are happening in that video. And another constraint was this algorithm has to be able to learn large patterns, learn small patterns, and basically what that means in a video, for example, is things don't always happen at the same time. In fact, the time between different events happening in video can be really large, it can be really small. So this algorithm needs to be able to relate things over a small period of time and a large period of time. And also because these kind of algorithms are usually pretty computationally expensive, they use a lot of RAM and a lot of processing power on the computer, it has to be able to run on a graphics processing unit. And GPUs are particularly useful because compared to a regular computer, they have thousands upon thousands of cores that allows you to do math basically at the same time on thousands of different levels. So you can run things very quickly. So I dealt with machine learning this summer. What is machine learning? Machine learning is basically a list of mathematical rules that allows you to describe how do humans view the world, how do humans learn from things that are actually happening in the real world. These allow computers to recognize features in images and be able to label images, and this same process can be applied to audio. You can recognize speech in audio. Most phones have that kind of technology nowadays. And there's two main kinds of this learning. You're either learning with a teacher, where the teacher's constantly telling you what you should be doing when you see a specific thing in an image or a video, or you're learning without a teacher, and you're letting the algorithm decide what it should be doing on its own. You're just feeding it in images. So as you can see on the right, we have this machine learning algorithm. We're going to feed in an image of a cat. We're going to see what it does. We might not even know that this is a cat, in fact. It could be anything. It could be a bagel. It could be anything. We're going to feed it into this algorithm. We're going to see what it thinks. So the algorithm thought it was a cat, and that's pretty good. And that gets really useful when you have a lot of images, for example, in Google search, when you don't necessarily know what the image is, you just have the image. So if you can feed it into this kind of algorithm, it can tell you what it is. But this is applicable to video as well, and more specifically, self-driving cars are becoming a really big thing nowadays. And if you can feed in a video, and that video can say, hey, there's a person walking right here, and maybe in 1 second, he's going to be in front of the car, so you want your car to stop. So machine learning is really important for that. The kind of machine learning I dealt with is using artificial neurons to model the structure of neurons in your brain and model how those neurons connect to actually allow you to learn. So the way that the artificial neuron in software works is you have a whole bunch of these inputs. You can think of those as other neurons. They're connected to each other in all sorts of crazy ways. Those neurons send a signal into this artificial neuron, this one neuron. That signal is weighted based on how important that neuron thinks that signal is. And you can actually tweak those weights. That's how artificial neurons are able to learn. Then you combine them together, and then you squish it between -1 and +1, and that's the activation of this neuron. You can kind of think that's how much the neuron is certain that this input it's getting might be a specific feature in your image. It might be a person waving, or somebody saying something. It's how certain the algorithm thinks that it saw something. Single neurons by themselves are very useful, but they're also quite limited. When you have a single neuron, it does a linear classification. It can find a line of classification between two different types of data. Your blue dots might be a tree, for example. Your red dots might be like a dog. A single neuron can find a line between those, but you don't always have data that's separable by a single line. In fact, when you have data like this, there's not really any good way you could put a line through that and it would be able to give you accurate results. So what are we going to do? Well, the common solution is, following biology, is to actually include more and more of these neurons and more layers. And actually, the cool thing is that you can create an artificial neural network where you have a bunch of these neurons in different layers all connected to each other. And once you have a bunch of those lines that best fit, it actually creates lines out of the end of the network that aren't linear anymore. They can be any shape. They can be a circle, as we saw with our previous slide, or it could be any possible shape. And the benefits of an artificial neural network is it can learn really complex patterns, although there are some downsides. It requires a significant more amount of computation on your computer than a single neuron does. But that could also, you could work that into whatever project you're working on, because having it in layers in this kind of architecture, it allows you to put it in parallel. So that's where the GPU came into play. So as you can see, putting it on a graphics processing unit, making it run in parallel isn't actually always good. It really only benefits you once you have these humongous networks, because then you can run a lot of computation in parallel. But when you have just a small network only doing a linear or maybe just a simple curved classification, you don't want to have it on a GPU. But what this also shows is that when you want to learn more complex data, like in a video, it requires a larger network. And also, something that I found with these networks, when they get larger and larger, the training time for these networks to actually get them to learn something, because it takes a human a while to actually learn something. These networks take a while to learn something as well. And a common amount of time that it was taking these kind of networks that I was working with was 5 or more days, just sitting there, the algorithm running on this supercomputer. So I invented an algorithm that I was testing throughout my project. And I compared that algorithm to the 2 industry standard ways of learning stuff in a video and learning speech in audio. Those 2 types of architectures are called long short-term memory, which kind of simulates how, as a human, you're able to dynamically learn something and then forget it when you don't need it anymore. And then something called the time delay neural network is the other architecture. And that basically is the same thing as a regular neural network. You just got these layers of neurons, except you can feed in multiple frames in a video at the same time. You kind of think of it's got a window that it is processing, a window of time at once. But these have some pluses and minuses, some downsides and some positives. So long short-term memory can basically remember things indefinitely. But the problem with it is it's really complicated, and it doesn't really run on small devices like a phone. So you wouldn't really be able to have something like this running on your cell phone. So that's a limitation. And it also learns moderately slowly. And the time delay neural network, on the other side of this, it learns pretty quickly, and it doesn't really fail at learning pretty often. It's a fairly consistent algorithm, but unfortunately it doesn't remember things forever. It's pretty good at forgetting the things that you're teaching it, and you don't want that for an algorithm. It also has a very simple structure, but when you're trying to feed in video to this structure, it actually gets large very fast, which again increases computation. So my motivation for my design that I came up with was something that learns significantly faster, so you don't have to train it as much. And I also wanted something that wasn't as computing intensive and took less time to actually say somebody's saying the word "the" or somebody's actually producing an action in a video. I wanted a faster algorithm, so I came up with this hypothesis that I built and used to construct a neural network. My hypothesis was the idea of, instead of layers in these networks only being connected to the layer directly in front of them, you allow these connections to actually go everywhere in the network, everywhere that's in layers ahead of where you currently are. And I'll show a diagram of how that actually works. And the only way that can actually learn patterns in time is when you allow there to be a delay. So what is this delay? Well, here is the algorithm that I invented. It has layers like a regular neural network, except it has an input layer, an output layer, and these hidden layers are not really layers. I refer to them as hidden neurons, where they're in between your inputs and your outputs. But what happens is when you feed in a number into this network, and that could be a pixel in an image, or I guess on a more abstract level, that could be the position of somebody's hand as they're going about a video. That's fed into the first node, and after a delay of 1 second, it goes forward everywhere ahead of itself in the network. And that keeps happening for the next couple time steps. But the intuition by why this can actually learn things happening over time is when you get to that last node, there's more than one point in time being represented there. And that's important because information is flowing through the network at different speeds. So you don't have to have very many neurons, like this shows, but you can still learn things happening over time. So it's significantly less complex than the other two architectures. So if you actually draw out all of the connections here, this is what it would actually look like. I'm not including the one on going from the direct diagonals and the input and the output layers, but that's almost all the connections there. And I called it the seriform neural network. And the idea from the seriform neural network, it's a term from biology that means resembling a saw shape or a triangle kind of diagram. And I wasn't able to actually include the image that inspired me to name it that, but if you wanted to know why I came up with that name, you can talk to me in my poster presentation coming up next. So I tested this network with the other industry standard methods that I also built. The first test was how fast could it actually learn. So I created this test example of a binary sequence. You can kind of think of that as there's a black image, and in that black image there's a white pixel moving to the right and moving to the left. And the algorithms are going to try to figure out which direction is that pixel moving. Is it moving to the right or is it moving to the left? And I plotted the amount of error that these networks had. And the amount of error is basically how much is it classifying it correctly, how much is it not classifying it correctly. So as you can see, I plotted these results out. And the network architecture I created actually performs the best in this circumstance. In fact, it learns the quickest out of all the networks by the third training iteration that I did with the network where I teach it. It actually is almost completely accurate, almost completely to zero, and significantly better than the other two architectures. I also did another experiment where I replicated the procedure of the first experiment with the same testing parameters, but instead I measured a couple of computing resource kind of indicators that would basically tell you how much of your computer is it using, how much processing speed is it using. So first I plotted execution time. So you can see that my network isn't the fastest executing, but it's nearly the fastest. It's very close to the time-delayed neural network, and it's also significantly better than long short-term memory. I also measured the amount of squashing functions, and basically you can think of that kind of as its own neuron. How many neurons are in the network? So you want less neurons in your network here because a phone, for example, wouldn't be able to have 1,000 neurons. It would only be able to support 10 or 100 of these because it doesn't have enough processing power. So smaller is better. And again, it's tied with the time-delayed neural network with the amount of neurons. And then the last indicator I measured was the amount of connections and weights in the network. How many things is it actually trying to train? And this is another measure of how much computation it takes. And again, the network I came up with is the most efficient here. So the results were really interesting. It shows that the architecture that I created actually, it learns faster and it requires less computing resources than these two methods that are currently used in the industry for self-driving cars, speech recognition, and other temporal kind of tasks. And also, it's faster, it could potentially be faster at pattern recognition in video. So I didn't actually test it on a video over the course of my internship. So that would be an idea of something that we could do in the future, because if it's capable of recognizing gestures in video without using very much computing resources, you could have it on a phone, and that's not currently able to happen. So again, there's more work that does need to happen on this algorithm for people to get a feel on how to actually implement it on different kinds of tasks. So I plan to actually implement this within the next year on some smaller devices. I had it running on a server through my internship. I plan to run it on a mobile phone and an Arduino. And again, more testing is needed on larger scales. So for my project, I'd like to thank Dr. Christoph Teuscher, who I worked under in the ECE department of Portland State University. He provided me a lot of amazing resources and papers for me to read over the course of my internship. And I'd also like to thank Portland State University for providing me the laboratory that I've been working in and designing this architecture in over the summer. It's been really invaluable to me. And I'd also like to thank Saturday Academy and all of you for coming and attending my presentation. Having the opportunity to work with these kind of algorithms, especially before I'm in college, has been very, very valuable for me. It's going to help me all the way through my career, future, and life. So thank you.
All right, we have a couple of minutes for questions. Does anybody have a question for Brandon? Anything that stuck out they want to ask about? It's a pretty technical talk there. It's pretty impressive. What was the most surprising thing to you about your internship? What caught you off guard, or what you prepared for?
Well, I really liked how I was allowed to be really creative with the direction I took it. The original task of the internship was just to work with neural networks and work with modeling how they actually learn things like image recognition, which in the machine learning field is a relatively simple task. And through talking with the professor, I was allowed to take that really beyond that task and explore things like videos and speech and eventually come up with my own algorithm.
And what was your biggest challenge in coming up with an algorithm? At what point did you feel the most resistance to forward momentum?
I guess the thing that took the most time was definitely keeping myself knowledgeable about the current research that's going on in the field. There's a lot of research papers that colleges are constantly pushing out and publishing in the field, so you always have to keep yourself updated on that. And it can be frustrating at times when you're building your own algorithm. There are no other resources really about formulas, so you kind of have to build it as you go. And when it doesn't work at first, it can make you a little bit discouraged.
And had you worked with algorithms even remotely like this before?
So before I got the intuition behind my seriform neural network, I was first working with just regular artificial neural networks, as I described in my slides. And through working with those, I kind of saw ways I could make improvements.
Anybody else? Yeah.
So I don't know a lot about this kind of technology or whatnot, but where can this actually be applied in the real world if your algorithm was to be used in the daily world?
So the thing that makes it a lot better than these other kinds of algorithms is it doesn't require as much computing power. So a lot of machine learning algorithms can only be run on a supercomputer, and you don't have that kind of computer in your car, for example. You don't have that kind of computer on a mobile device. So this kind of algorithm that doesn't use as many resources on your computer would open up the door for recognizing things in video and recognizing gestures, for example, recognizing sign language, and even more accurate speech recognition, and even more accurate cars that are able to tell what's in front of them. It opens up the door for a little bit of that. Any other questions?
Has Google called you with a job offer yet?
No. No.
All right, thank you very much.
Thank you.